Hello, everybody. Thank you for being here. Using an high-performance storage is not really a trivial task. We see that now you have a good infrastructure set up as described, and you've got to use it, and that's really not a trivial task. So I want to focus on the storage side, not on the computation side. I will try to keep it very basic, but focusing on few important topics that I consider fundamental for the good operation of a system. So let me introduce myself very briefly. I'm a system administrator and engineer here at FMI. And if you remember Dean's presentation about the DDN storage system and setup and mirroring and snapshots, that was most of my work, and including assisting users in using the new system that we introduced, which was quite a dramatic change compared to the system that we had before. So the first thing that is fundamental to know when you're using a high-performance storage is that you should forget what you know about the conventional storage you use every day on your computer, on your workstation, even on your mainstream server with what you consider a pretty fast and big storage. So the reason is because there is no relation between the two. Let's say, so there is no standard in petabyte scale storage systems. What you use in your workstation and your computer is normally a standard hard disk drive or an SSD, and they all have the same interface, the same protocol to speak to the computer, the same form factor, the same power consumption. Even the speed is not that different if the memory technology used by the storage is the same, right? So with high-performance storage, it's not like that. They are all different. They are completely different in the software, in the protocol they use, the hardware they use, and different systems can yield very different performance with the same workload, while standard system would deliver more or less similar results. Also keep in mind that due to the size, they are remotely connected, and this changes a lot on the way the computer and the storage are communicating compared to when the storage is inside the computer. Also, when you increase the order of magnitude of quantities, like by 2 or even 3 order of magnitudes, you might reach bottlenecks that you are not able to normally reach. One common one is the file size, since you just have a lot more space now, but your data format is the same, and you just have many more files because you can store more data, and you might hit bottlenecks you were not able to before. Another thing that's very, very important to know when you're using an high-performance storage is to know its limits. So since they are not standard, the limits are not the same for each system. So if required, get in touch with the informatics department of your institution and get to know your system, because different hardware and software used by the system will limit speed, capacity, file numbers, any kind of operation the storage can do. And of course, having a little bit of knowledge in the common problems that you can encounter when using an high-performance system and how to avoid them can greatly help your life without, and help you not wasting time. So 1 year ago, we purchased the new system. We put it in production, and this is, as you already saw, the typical data workflow. We have a centralized approach where data is coming in from any source, really. Typically is an instrument like a microscope here. And once the data is on the system, it's centrally accessible from any resources, from the computer workstation, like the user laptop, the computational resources, the VM infrastructure, or eventually a cluster if you have one, and even the tape archive, so that once the data is not more useful, can go to tape very quickly. We are pretty happy with this new setup. Most of the stuff works without problems. We choose a DDN GS14K-X system for this, which is one of the fastest storage currently available, at our humble opinion. And it's also the top of the line for DDN offering. So we thought, okay, as Dean said, performance first is our top priority. We should be set and good to go. Well, when stuff works as expected, yes. When stuff doesn't work as expected, Not really. That's, I think, the most common problem that we have to assist our users with is that their workflow, for some reason, is not performing as expected. It's taking too long to process. So based on our experience, I will tell you something based on real cases that we had here. Now, keep in mind that all the numbers I will tell you are based on the system we have, unless otherwise stated. So they are very specific to our use case, if you want. One of the first encounter of these problems was when we started benchmarking the proof of concept system, and we started playing around with high continent screening data sets. So those are data sets where the files are usually 10 megabytes in size, and you can have a large quantity of them, between 1,000 and even millions sometimes on some data set. So reading the data, copying the data around, trying to emulate what the typical workflow is, was yielding a rather underwhelming performance of 50 to 150 megabytes per second. So this was on multiple systems, not just on the one we had. We had multiple proof of concepts, that they were all within this range, all of them. Now, this is a bit disappointing, is it? So the brochure of the system, they are supposed to be very fast. They're supposed to be able to go up to 50 gigabytes per second, and you are getting out 50 or 100. So your SSD on your computer goes fast. So it is disappointing. Is it actually? Well, spoiler alert, no, it's not. And this is how I want to convince you about this fact. So I think that the topic of file size is very important. Maybe the most fundamental topic on high-performance storage systems. So I made an effort to make an analogy with something we are all really familiar with, and this is relocation. Everybody of you at least probably relocated once in their life. Okay? So I will use boxes and books as the representative of big files and small files. So let's do a mental experiment here. I'm a physicist, as they say. So let's do a mental experiment. Let's pretend I have a box and a bunch of books here in this room with me. And I want to relocate them. I want to bring them down to my office at the ground floor. We are at the 5th floor here. Let's also set one rule that I can only carry one item at a given time, because this is how computers are working. So a single-threaded program, a non-parallel program, will be able to do only one task at a time. So let's pretend I am a single-core CPU, okay? And I can do only one thing at a time. So let's move the big box. I take the big box, I go to the elevator, I call the elevator, I wait for the elevator, I go into the elevator, I go down, I exit, and I reach my office. I relocated the big box. It took about 2 or 3 minutes, okay? Now, let's move the books. I pick up the first book, I go to the elevator, I call the elevator, I wait, I go down, I go to my office, I put down the book, then I rush back to the elevator, call it back again, go back up, pick the second book, and so on, and I cycle until I do all the books and I am done. So this can take up to even an hour for just 30 books. I think we are all thinking that this is a very inefficient way of moving books, even just between floors in the same building. This is exactly what happens with your files. Your files are in one storage, in one room, and you are just bringing them to another system, a computer, your workstation, your servers in another room. That's exactly the same, right? So it's very inefficient to do it one by one like that. So nobody would ever do that in a real relocation. What you would actually do in a real-world relocation is you will pack your data. You will put the small files, the books, into the box, into a big file. So just for a comparison, when you try to transfer, so as a comparison with the 10 megabytes files I was talking earlier, when you transfer 1 gigabyte files, so just 2 orders of magnitudes bigger, you can easily saturate a 10 gigabit Ethernet link, and you can reach speeds between 2.5 and 4 gigabytes per second, gigabytes, with InfiniBand network. So that's a pretty substantial difference right there. Now, you might say, okay, but 10 megabyte files are not small, so your argument is invalid. Well, remember that I said that you reach bottlenecks when you change the order of magnitude of the system, both the speed and the size. You change, you find new bottlenecks that you were not even able to reach before. So in this case, we just shifted the size of the storage and also the speed of the storage. And the concept of small also shifted with it. Let's think about it. If you can read 150 megabytes per second from your standard hard disk drive, a magnetic hard drive, you are pretty happy. Why? Because that's the limit of the system. That's the maximum read speed you can get out of a magnetic hard drive as of today, right? But when you talk about a storage which is 1,000 times bigger, well, a 10 megabyte file looks 1,000 times smaller, right? So that's why 10 megabytes files, while they might not sound very small, they are actually very small when you talk about a 1 petabyte, a petabyte scale storage system, right? So yeah, 10 megabytes are small, but not extremely small yet. You can still manage to do your work. But they are small enough to be an obstacle to reach better performance. Another natural solution to the problem is to parallelize your workload. So instead of bringing down one book at a time, you can bring many, or you can have more people doing the work, which is even more similar to how a computer works, right? So again, as a comparison with the 10 megabyte files, with 16 parallel processes, we can again saturate the link of 10 gigabit Ethernet network. And with InfiniBand, we reach a speed of about 2.5 gigabytes per second. Further increasing the number of processes can bring up again to the 4 gigabytes per second performance. However, this can be complex. It's harder to parallelize the code compared to having larger files. So the code I used for this benchmark was way more complex than the code I used for the previous one with the big files. I think this one was at least 150 lines of code, and the other one was probably 10. So just to give you an idea, the line of code is not the only good method to do this, because it took also longer to get the code right. Because parallelism means synchronization, resource contention, so it's not easy to get it right. Of course, you can combine both solutions into a single one. So you can, try to make your data a little bit larger, not extremely larger. And you can also parallelize a bit. The two things can help, hide each other's weaknesses, and you spend less time coding and tuning a complex code, and you can get the most, let's say, bang for the buck for your performance. Also, if you have a lot of files, of course, there is a problem of organizing them. If you just put them all in one folder, and you have a file with millions of folders with millions of files, this can be a bottleneck. For example, if you, in such a case, you might wonder why your simulation works pretty well with a small data set, and it slows down exponentially as you add files to it. This might as well be one reason. Even if you can swear that your algorithm should scale linearly because you used a very efficient one, so the exponential slowdown doesn't make any sense. Well, this can be the cause of it. If you saw the movie Yellow Submarine, you might be familiar with this scene where old John was trying to find the Beatles in the multidimensional hallway with so many doors. Well, this gives you an idea of what's happening in the computer when you have all the files in one folder. The computer has to go through a very, very huge list of entries to find the files you're looking for. And so this is, if you want, this is a system limit. So this is a limit to change system by system. Some system will be able to handle quite nicely larger quantities of files in the same directory. Some system will fall down with a rather small number. It's hard to give a number, so because of these reasons, because it's very system dependent, but I would say to play safe, just use 10,000 files per folder. For some selected system, I will go up to 100,000, but I will never exceed that when possible. So speaking of limits of the system, knowing your limits is, as I said earlier, very, very important. And I want to show you why with a comparison of these two POC systems that we had when we had to choose which storage to purchase. So the two systems are, one is an EMC Isilon and one is the DDN GS7K. And this is a self-homemade benchmark that is supposed to simulate some part of a simple pre-processing utility for high-continence screening data. So this is a part of a pre-processing utility. We stripped out all the computation and kept only the input-output, okay? So we did that both single-threaded and multi-threaded. In the single-threaded, you can see that the results are pretty much flat. The EMC is slower, but other than that, there is no much difference. The protocol, the network used, InfiniBand, NFS, doesn't matter. In the parallel one, the situation is a lot more interesting. So we can see here, I can tell you that having more experience than these two systems, NFS in general is absolutely not parallel friendly. Don't waste time parallelizing your code if you have an NFS-based storage, because this usually doesn't yield much performance gain. With the exception of the EMC storage, they actually manage to deliver. Parallel file systems like GPFS and Lustre are much, much better usually for these kind of workloads, and they will obliterate your NFS and Samba performance very easily. InfiniBand can also be a huge help, of course. Faster network, if that's your bottleneck, then it will greatly help. This is one test case only, of course. Your results might be very different, and very quickly this is an example of what might not work very well. So if you have a lot of, if you have a program, a single-threaded program writing a lot of synchronous files to the disk, GPFS will perform very poorly, while NFS, due to a different caching model, will be a lot faster. Now, note that this second line is using InfiniBand. InfiniBand doesn't help either in this kind of workload. Another example is when you can do a lot of random reads. So the blue dots are with 10 gigabit Ethernet NFS, and this is GPFS with the orange one. Of course, in this case, though, using InfiniBand greatly help you increase the performance, and you actually gain a lot. So to summarize this is to say, if you know the limits of your system, you can avoid wasting time. For example, if you have an application like this, avoid wasting time with GPFS, or if you have a parallel program, avoid wasting time with NFS. And when, if you know the system, you can foresee the bottlenecks and work them around or remove them, such as switch to an InfiniBand network on some workload to get a better performance. Thank you for your attention. Any question? I'm around as well as Dean, so feel free to hook me up later during the breaks as well.